All right, we're going to go ahead and get started. That was really fun. USB-C connectivity is great. So because of that, my talk is going to be 5 minutes shorter. When I practiced this, it took me 50 minutes. So apologies if I go really fast through some of this. So welcome to my talk, Adventures in Conformance. I'm Aaron Crickenberger. I work for Google as of a couple months ago. I worked for Samsung SDS before that. I started working on Kubernetes prior to it launching 1.0, around the same time Janet Kuo started. I started the SIG testing group. I started the conformance test framework around version 1.2. I'm currently a member of the steering committee. But the reason I want to talk to you today is as a member of the Kubernetes community. So when I say we, I'm not talking about my employer, I'm talking about all of us. You are all members of the Kubernetes community as well. So I'm going to talk about what we want and what we should do a lot. Okay. So Dan talked during his keynote about how Kubernetes has crossed the chasm of uncertainty. Early on, we realized there was this primordial soup of container orchestration implementations, and we needed one of them to win to become the de facto standard. In order for this to happen, the Kubernetes project chose to prioritize moving fast and intentionally take on technical debt in order to do so. This meant that very often, cool. I won't step on anything. This meant that very often we ended up dumping a bunch of code into a single repository and not spending too much time focusing on implementations. Since we have crossed the chasm, we are now trying to make Kubernetes boring, as Janet said in her keynote. So a lot of this involves defining extension points and extracting functionality out of Kubernetes. So this is why we now have container networking interfaces, container runtime interfaces, and container storage interfaces. We're also working to extract the cloud provider functionality outside of core. And as we do this, we are focusing on stability and reliability of Kubernetes as a whole. We don't want to add new features while we're doing this. And it's important through all of this that we focus on portability of workloads to make sure that if I write an application and deploy it to one Kubernetes cluster, that it works just as well on another Kubernetes cluster. This is how we grow and mature as a project. Finally, once we make Kubernetes boring, we want to keep it boring. And this is where conformance comes into play. Conformance is the boring thing that allows cluster operators to know, is my cluster a certified Kubernetes cluster? Is it conformant? Did I deploy it the right way? Is it configured correctly? It will allow application developers to know, is my application, is my workload actually portable? Do I use the features that have been tested by conformance? Or am I using some alpha or unstable features, like a projector? And it will allow Kubernetes developers to know if their feature is ready to be GA, generally available. Man, this is really annoying. So Dan showed a wonderful slide where he showed that there were over 77 vendors who had their offerings certified as conformant. So clearly this program has been successful. It's okay. But so the conformance program is really all about defining what a Kubernetes is. A lot of people, when they talk about Kubernetes, will start talking about pods and replica sets and limit ranges and resource quotas and ingress controllers. But really, a lot of people think about Kubernetes as a set of behaviors or functionalities. I don't care that I have a deployment. I don't care that I have an ingress controller. I care that I have an application which will automatically scale in response to demand so that traffic will route from the outside internet to my pods through a service, and the pods will be scaled via a horizontal pod autoscaler. And the whole thing will be managed by a resource quota and limit range. All that to say, I don't care about pods. I don't care about replica sets. I don't care about ingress. I care about the behaviors that are visible to an end user. And this is what conformance means. It means we want behaviors that end users can see that work on any given conformant cluster. It's important that I'm talking about behavior and functionality here, not just API interaction. There's a lot of behavior and functionality I want from Kubernetes that is more than HTTP requests and responses. It is running a container and seeing that container do things, write data someplace, make requests to other services. So it's important that we look beyond just APIs. Another way of thinking about this is architecturally, we like to break Kubernetes up into these layers, and the bottom layer has many different components which can vary, including the container runtime, or the different kinds of networking, or the different kinds of volumes we can use. On top of that sits the nucleus layer, where things like config maps and pods will live. Fundamentally, if those don't work, all of the other layers on top can't work either. And when we focus on conformance, we focus on these three layers. These three layers have to work regardless of what changes underneath of them. And if these three layers work, effectively everything on top of them will work. So, okay, we have these conformance tests, and we have a certification program that uses them, and we have 77 vendors who are certified and conformant. But what does that mean? I hear people say we use these, but they barely cover any functionality. Is that true? What do we mean when we say that? So I want us to, as a community, we need to add more tests to exercise more functionality so that conformance covers meaningful behavior. I want us to focus on pod functionality because the pod is the fundamental abstraction of Kubernetes. I think Brendan Burns said this well in his keynote when he talked about how people cared about where the pods ran, not necessarily about the nodes or anything. We want to I also talk about measuring functionality and covering functionality. That's difficult to measure directly, so instead, let's measure proxies for that. Signals that tell us if it's headed in the right direction without being able to actually measure it. So what API endpoints are being hit when we run end-to-end tests? And what code is actually covered or executed when we run those end-to-end tests? So to add new conformance tests to Kubernetes, it involves writing end-to-end tests because those are the best representation of a user's view of how Kubernetes behaves. We then need to document what that test does so we understand the behavior, and then demonstrate that it meets a few simple requirements. I don't have time to go over all of these, but please feel free to ask at the end. But essentially, these are requirements that tests work across all Kubernetes clusters. So they must be using features that are standard and default and must work for all providers. They ideally should be capable of running in parallel. They should not require direct access to direct access to network interfaces or run as root. And I think importantly here, we should require that the tests work without internet access. We think an air-gapped Kubernetes cluster that doesn't talk to the internet is just as conformant as a Kubernetes cluster that lives in the cloud and is soaked in the internet. Finally, we want to make sure that that test is consistent and is signed off by the architecture special interest group of Kubernetes to make sure that the test describes what we think Kubernetes to be. You can see that these bars go up and to the right. That's great. I joined Google and started working on this around version 1.11. So I like to think that I had an impact. And each of these bars corresponds roughly to a quarter. So version 1.9 was December of last year. Version 1.13 is the release of Kubernetes we are working on right now. And I think we are trending in a good direction. If you want to know what the specific tests are, here they are, but I don't have time to walk through them. Really, the point of these slides is to show what those bars look like as text, and to brag about that, I can't even fit the tests on this slide. There's so many. But really, when I compare the number of conformance tests to the number of tests that we run to define as release blocking, there are many more tests that are release blocking. We run hundreds, if not thousands, of tests to define what a Kubernetes release is, and many of these tests do include features which are optional or do require root access. It seems, though, that there might be some functionality from those tests that we're not covering with conformance tests, and we have room to improve. So next steps for adding tests are to add more functionality, cover more functionality around pods. More tests around workload APIs, like deployments and replica sets, might help, but we need more direct coverage of pods and the things they do. The things we're working on for improving the requirements for conformance involve tagging the tests that do things that are wrong so that we can talk about those. Identifying other constraints we might want to add to those requirements. So today, I believe we want to say that conformant clusters must have multiple nodes so that we can sufficiently exercise deployments and replica sets, things that offer zero downtime deployments, rollouts. And we want to develop profiles which have optional features. So we may see a profile on top of additional conformance that says this cluster can run Windows containers. Or we may say that this cluster has cloud provider functionality. I don't care which cloud you're in, I believe your cloud has a load balancer as a service that you can use. So I'm about to show you a bunch of data. Just take my word that you too can do this. This is how we create clusters and run them in Google's CI or in the Kubernetes CI. This is a pull request that I submitted to the conformance repository to make sure that I got this certified as conformant before giving this data to you. All of the results that we run as these conformance tests are posted on a website we have called TestGrid, where you can see we have conformance results for Google Cloud, OpenStack, VMware is submitting results up there. This is proof that the conformance tests are run every hour of every day. Here I have clicked through and chosen the dashboard for the conformance tests for version 1.13 of Google Cloud. I'm clicking on a specific result, and I'm seeing the results from this test. The results that I care about are a JUnit XML file and some log files. We dump log files from all of the components, as well as all of the nodes. Using these audit log file, I can use API Snoop, a program developed by the CNCF, to compute API coverage. API Snoop can parse Kubernetes Open API spec to find all of the possible endpoints. An endpoint here is an HTTP verb and a path. So for example, posting to a pod's endpoint in namespaces to create a pod as a single endpoint. We can then parse the Kubernetes audit log to find all of the endpoints that have been hit as a result of the conformance tests. Using this, we can answer questions such as, what are the total endpoints that we can cover? And what are the actual endpoints that we hit? So here is another graph with shiny colors. The red is the latest release, and you can see each release has had more API coverage by percentage. So we're making great progress. You can also see that there's been a lot of increase in coverage for version 112 and beyond. Behind this white box is the API coverage offered by those release tests, those big blue bars. Any idea how much additional coverage those provide? It turns out it's only about 10% more. It's not a whole lot. I also just quickly want to explain the reason those bars jump up so high is we discovered that there are deprecated endpoints for watching that we don't need to cover because conformance tests shouldn't be exercising deprecated features. If I want to try helping out, perhaps I want to look at API coverage in terms of which APIs got hit and which APIs did not. The red ones didn't. This doesn't seem very easy to understand. How can I make better sense of this data? So this is a graph produced by API Snoop. I call it the sunburst graph. The inner ring denotes the different API levels. Green is stable, blue is beta, red is alpha. Version 1.9 of Kubernetes was the first version that had audit logging turned on by default. So this was the first release of Kubernetes that we could use API Snoop to measure. And you can see we had about 24% total API coverage. By version 1.12, you can see the impact we had by removing those endpoints. We also moved a number of end-to-end tests that were run just for the kubelet and turned them into conformance tests for the whole cluster. This was also the first release where we could parse the user agent from the end. The user agent was provided by end-to-end test. So we could see which API coverage was coming from end-to-end directly. Those are the darker colors. And which API coverage was coming from the Kubernetes cluster directly. Thus far, we have promoted even more tests, and that's great. But if we look just at the API coverage from the end-to-end test, it seems like we're not making a lot of progress. This is why we think that it's important to not just measure the API coverage coming from running the tests, but also how Kubernetes as a distributed system behaves while running tests. If we look at the API coverage that could be available to us by running the release tests, we could have a fair amount more. By setting the user agent to not just the name of the program hitting Kubernetes, but also the test names, we can answer the question, which endpoints are hit by which tests? Which endpoints are hit by the most tests? Here I can see that many endpoints are hit by all of the tests all at once. These endpoints probably don't mean anything to me. So let me instead look at the endpoints that aren't hit by all the tests. Take my word for it, the endpoints that are hit the most involve creating and scheduling pods. And this should not be a surprise. End users want to create and schedule pods, so that's how we write a lot of our tests. I wanted to look at a specific test called proxy version 1 should proxy through a service in pod. I won't bore you with the details. This is clearly very easy to understand. So instead, I will walk through what the test does in terms of API access. This is the reason that all of the endpoints get hit all of the time. We create an API client that explores every possible resource that the API offers. I don't care about this. This looks more useful. I create a namespace, I create my Kubernetes resources, and then I start hitting the proxy endpoint. But it seems that I'm only using the get verb to hit the proxy endpoint. So the lesson learned by looking at the way a single test interacts with the API is that there are 6 different HTTP verbs that this test is not using. This test is also only hitting /proxy instead of /proxy, /with, /subpath. Right away, I found 13 additional API endpoints I could cover by writing new tests. Some of the next things we're going to do with API coverage include looking at the OpenAPI spec from a live Kubernetes cluster to get API extensions, such as scaling policy and metrics. dynamically configuring the audit log policy so that we don't have to SSH to the cluster to get the audit log. And the thing I'm most interested in is covering more than just verbs and paths, but also parameters and the fields of all resources on the bodies. So looking at line coverage, many of you probably know that Golang supports instrumentation for unit test line coverage or code coverage. But the problem is this only gathers code coverage for unit tests, and it only outputs data when the unit tests finish. What if we made Kubernetes a distributed system of unit tests? What if each component of Kubernetes was just a unit test? And then what if instead of writing the code coverage data once Kubernetes shut down, what if we wrote it to disk every 5 seconds? In this way, we could deploy Kubernetes, gather the coverage data before we run our end-to-end tests, run our end-to-end tests, gather the coverage data after, and then do some math. We wrote a tool called Gopherage to allow us to merge all of the code coverage from the various components, take code coverage from 3 different kubelets, a scheduler, a controller manager, an API manager, merge it up into before and after, and then diff the 2. Finally, exclude a couple packages we know we don't care about, such as a cloud provider, since this is conformance. And now we have a coverage file that any tool that knows how to use coverage files can use. So some of you may know that Go generates an HTML report that shows which lines of code are covered. On the right is code that is covered by the conformance test. There's a lot of red there. It's not covering very much. On the left is that same code, but being covered by the release tests. Maybe this is a file we should look at more. But looking at files seems very boring and difficult to traverse and search. So what if we instead wrote our own report that allowed us to traverse a hierarchy? Gopherage does that. Gopherage allows us to see that looking at the lines of possible executable code, today we cover 28.5% of Kubernetes. That's a lot of red. Why so much red? Well, end-to-end tests can't always exercise the failure conditions. In unit tests, it's possible to fake or pretend to hit every single error condition, but in the real world, you can't always cause that to happen. Further, I should point out that the release tests only cover 33.5% of Kubernetes. So again, there's a lot more tests we could be writing. But it's not all red. If we look at, we can start to compare code coverage over time, and you can see this is difficult to read right now. We are working on ways to reduce the noise. It's not all bad, though. You can see the code for the kubelet to interact with Docker is mostly green. Conformance has a lot of interaction with it, as does the end-to-end tests. Also, here's an area or an example of gap in testing that we identified that we could not find with API coverage. On the left is the code that executes liveness and readiness probes against containers on the kubelet. It's green. It looks like that is fully covered. But if we look at the actual kinds of probes that can be executed, there are exec probes, HTTP probes, and TCP probes. And the TCP probes are not being exercised by any of the tests. Clearly, this is a new test case we can add. Finally, just for grins, I tried taking the code coverage file and uploading it to a service called codecov.io to see if I could generate any pretty graphs. They made this tree map here. It's all red. So it doesn't do any of the filtering that our other report did. It's making me feel like we could write our own version of this that maybe even linked directly to the files, so we could go from the big red square to the directory to the individual files. So I also feel like that test grid, all the green squares that I showed you earlier, we could put our code coverage data there as well to see how it changes over time. So how you can help? I really, really think we as a community need to be writing more tests that exercise pods and look at their behaviors. You can help us categorize the existing tests. There are many tests that seem to be slow or flaky that aren't categorized as such. You can run conformance tests against your own Kubernetes cluster. Many of you probably use Kubernetes today, and who knows if your cluster is actually conformant. If you are doing useful stuff and your cluster fails those tests, we should understand what we're not testing that works for you. Finally, you can participate in discussion about this at the CNCF Conformance Working Group or at the Architecture SIG, details of which I have linked in these slides, which you can find online. So I have a bunch of links if you download these slides. If you want to contact me, I am at spiffxp on all the things, Twitter, GitHub, Slack, SoundCloud, Tumblr, whatever. And there's my email address. I also wanted to congratulate Ben the Elder for his work in helping me put this presentation together. Catherine did the code coverage tools. Hippie Hacker and Zach Mandeville made API Snoop. They're giving a presentation, Hippie is giving a presentation about that next, which I highly encourage. And that's it. Any questions?